Today we discuss insect outbreak model, the Spruce Budworm model. And Spruce Budworm can defoliate the balsam fir and spruce forest with ferocious efficiency, which is a major problem in Canada. Can defoliate means destroy the fir tree and spruce forest. There's ferocious efficiency, which is the major problem in Canada. Budworm are moths that chew their way into tightly coiled buds of flowers and slowly eat them from inside out. So here, budworm are nothing but a moth, and they chew their way into tightly coiled buds of flowers and slowly eat them from inside out. And birds are the main predator of budworm. পাখিগুলো তারা বার্ডওয়ার্মগুলোকে শিকার করে নেয়। The budworm has stunning growth rate and can increase its density several folds in short time scale compared to the predator bird and hosts, that is fir and spruce trees like this. So the budworm growth rate can increase its density several folds. So budworm growth quickly, very quickly, compared to the bird or spruce or fir trees. So this is the budworm, which is the major problem in Canada, and the main predator of this budworm is birds. Now let us suppose n be the density of budworm at time t, and then its food limited growth can be represented by predation independent growth model. We consider this model, dn dt equals to rb into n bracket 1 minus n by kb. Here k suffix b is the carrying capacity, environmental carrying capacity, and which is assumed here a constant, and the parameter r suffix b is the intrinsic growth rate of budworm. Intrinsic growth rate of budworm, and this is the kb is the carrying capacity, and this. Now we include the effect of predation in equation 1. We include the effect of predation by birds. It is assumed that predation of budworm by birds depends on budworm which is called prey, and whose density is n, and its approaches to saturation value when n is very large. N is the density of the budworm. So we include here the term Pn, which is equal to Bn square by A square plus N square. And there is a approximate threshold value Nc, below which the predation is small, while above it the predation is close to saturation value. The predation term Pn is given by Holling 3 type functional form. Pn is equal to Bn square by A square N square. This is the Nc is the approximate threshold value Nc. We will later discuss details about the Nc threshold parameter, threshold value of Nc. So predation term Pn, actually mainly by bird predation, this Pn is equal to Bn square by A square N square, where A, B are some constant B is positive, the maximum removal rate of budworm due to predation, and A is positive, is the threshold value of NC. And we draw the graph of the predation. Here the horizontal axis is the density of the budworm, and Pn is the predation by birds of the budworm, and where here density increases, and then predation also increases. At when n is A, and suddenly change to predation up to B, and this predation is B and B by 2, and suddenly predation density is from the A to here near to 0. Density from the left hand side of A is density of the budworm is 0. The right side of A, point A, the density of the budworm is jump to B. So A is the threshold value. Note that the graph of predation is sigmoid nature. This is the sigmoid curve of this graph, and predation with density of the budworm. For n less than A, when n is less than A, when n lies here, when n is less than A, the predation is small. Predation is small. Predation is the height of the predation is small. And while n is the right side of A, that is the n is greater than A, it is switched on. That is predation is B by 2. On the point A is predation is B by 2, and right hand side is predation is jump to the point B, We can say A is the half saturation constant, which measures the density of budworm at which the predational removal rate Pn reaches to the middle of its maximum value B. Incorporating such predation term 1 in 1, the growth rate of the budworm may be represented by the model 2. So actually model is this, where dn dt is the growth rate, and this rbn into 1 minus n by b is the growth curve, growth rate, growth function, and this minus bn square by a square plus n square is the removal of the budworm, that is by birds. So this is the actual model for this insect outbreak model. Now here we neglect the growth of predator here bird, and the host, that is fir or spruce trees, as these occur at a slower time scale, because the growth of the budworm is higher, much higher than the birds, growth rate of birds and growth rate of fir and spruce trees. So we neglect here the growth of this bird and the growth of the fir and spruce trees. Here neglect here. We only growth, that is the density. We only here consider the density of the budworm here. N. Now we first the non-dimensionalize of this the equation 2. First we the non-dimensionalize of the equation 2. For this non-dimensionalization is the partial or full removal of the physical dimension from an equation involving the physical quantities by a suitable substitution of variables. And this has several advantages. The unit used in the analysis are then unimportant. It reduces the number of parameters to dimensionless groupings which determine the dynamics. And number 3, non-dimensional equation will provide insight on controlling parameters and the nature of the problem. Number 4, this allows testing model instead of the expensive large full-scale prototype. So for this normalization, equation 2 has 4 parameters. Notice that we had the 4 parameters RB, KB, B and A. Here A and KB have the same dimension as in proportional density. RB has the dimension is the time inverse scale, and B has the dimension of the n into time inverse scale. Proportional density but unit time. Now introduce the non-dimensional quantities. U equal to n by A and R equal to A into RB by B, Q equal to KB by A and tau equal to BT by A. These 4 non-dimensional quantities U, R, Q and tau. So here du dt is equal to 1 by A is constant dn dt. Here U is a function of t, U is also function of t, n is also function of t. Then from equation 2, A into du dt, B by A R into A into U bracket 1 minus A into U by AQ minus B into A square U square by A square plus A square into U square, and put this relation du dt is equal to 1 by A dn dt in the equation 2. In the equation 2 here, put this here in dn dt. In place of dn dt we put here this, and value of n replaced by this u into a, and dn dt is equal to a into du dt. Put this in equation 2, we get this equation, this divided by b, so a by b du dt is equal to r into u 1 minus u by q minus u square by 1 minus u square. This is equation 4. Now non-dimensional time tau equal to b by a into t, so d tau equal to b by a into dt. So du d tau equal to du dt into dt d tau by chain rule, and du dt and dt d tau from this relation is equal to a by b. So du d tau equal to a by b into du dt, and hence from equation 4 and du dt is equation 4 from du dt, replace du dt by du d tau, so we get du d tau equal to r into u bracket 1 minus u by q minus u square by 1 plus u square. The expression on the left hand side is called fu, function of fu say. So the equation 5 is the has the only 2 parameters here, the r and q. Here population density capital N is replaced by the non-dimensional parameter u, and time t replaced by the non-dimensional time tau, and there are also 2 parameters in r and q in place of 4 parameters in the equation 2. So here are dimensionless equation 5. Now we study the equation 5 for this model. Now we have to find the equilibrium points or steady states by equating du d tau equals to 0, that is f equal to 0. So we get the equation this, and the root of this equation, the value of the u is this, u equal to 0 or the second term equal to 0. Obviously this first steady state equal to u1 star equal to 0 is an equilibrium point steady states, and other equilibrium points are the positive root of the equation this, from this other roots from this, from the equation 6. It is a cubic equation. Obviously after simplification you get this is a cubic equation, and we can determine the existence of root graphically from this curve, from this equation. The equation 6 can be written as r into 1 minus u by q equal to u by 1 plus u square. Left hand side is per capita growth rate of the scaled variable u, per capita growth rate left hand side, and the right hand side is the per capita death rate due to predation. Per capita growth rate and the due to the scaled variable growth rate of the scaled variable u, and the right hand side is the per capita death rate due to predation by birds. The non-trivial equilibrium points exist at the intersecting points of the curves. First curve left hand side equal to say gu, so gu equal to this curve, and right hand side is equal to hu. So intersecting these two curves, we get the roots of the equation 6. Here gu is the straight line which meets the u-axis at q and vertical axis at r. And note that h0 equal to 0 and limit u tends to infinity, h equal to 0, implying that hu passes through 0 and approaches to 0 as u tends to infinity. Also, h dash u equal to 1 minus u square by 1 plus u square whole square, and h double dash u equal to and this. Thus, h dash u equal to 0 gives u equal to 1, and h double dash 1 equal to minus half, that is less than 0. So h has the maximum at u equal to 1. Further, h double dash u equal to 0 gives u equal to root 3. Thus, h double dash u less than 0 for 0 less than u less than root 3. Implying hu is the concave downwards in 0 less than u less than root 3, and h double dash u greater than 0 for u greater than root 3. Implying that hu is the concave upward in u greater than root 3, 1 point, that is approximately equal to 1.73. So here we draw the graph for this is the axis, horizontal axis is u, and vertical axis is function, and this is the graph gu function. So for this graph, this is the gu and this is the curve is the hu. So this is the graph for gu, this is the graph for gu r into 1 minus u by q. Here this is the graph. So here r constant, that is parameter, and q is also parameter. So gu equal to minus something into u, so it is a straight line, and this is represents the straight line, and h equal to u by 1 plus u square, and gives the represents this type of curve. So this is the hu curve and this is the gu curve, and intersecting these curves gu and hu intersecting at 3 points, this point, this point, and this point. So this point, this point, and this point, and draw the perpendicular on the u-axis. So this is the u1 and this is the u2 and this is the u3, and this is the three roots of the equation 6 of the equation 6. This u1, u2, and u3 equation roots of the equation 6. This is the equation 6. This is the equation 6. Here equation cube equation roots, we find the roots of this equation 6 is determined by the graphical method, and so this is the equation of the root 6. And the phase portrait, that is u and fu. Fu means du d tau, du equation from 5, equation 5 is du d tau. This is the du d tau versus u. This is the phase portrait of the equation 5. For this phase portrait of the equation 5, this along the vertical axis is du d tau, and the horizontal is the u. So we get this graph, that is u into gu minus hu, if u is equal to this, because expression of fu is here equation 5. From the equation 5 we get from equation 5 du d tau equals to u into r into 1 minus u by q minus u by 1 plus u square. So this function is called gu and this function is called h. So we write du d tau is equal to u into gu into h. Now this is the graph for fu, that is du d tau. This graph is this first equilibrium point is 0, and second equilibrium point u1, third equilibrium point u2, and fourth equilibrium point u3. And first equilibrium point u from the u equal to 0, and the u1, u2, u3, the roots of the equation of this equation of the term of the inside the bracket equals to 0. So we get the 4 equilibrium points. Clearly we see that this origin 0 is unstable, but u1 is stable, u2 is unstable, u3 is stable. This is the phase portrait. The number and location of the intersection of these curves depends on two parameters, r and q. During the Budworm outbreaks, and it may be assumed that environmental carrying capacity q, non-dimensional is to k, non-dimensional kb, varies considerably. gu and hu can intersect either at 1 or at 3 points depending on the values of q and r. If r is increased, that is the rotation occurs clockwise, then the points u1, u2 move towards each other and coincide for some value of r, where the system loses its lower equilibrium u1. If r is slightly increased further, then there is only one point of intersection u3 and hence one equilibrium point. If we move away of the straight line gu from origin, then obviously clearly see that this straight line intersects the curve hu at the only one point u3. So for this existence of one equilibrium point is this, when the phase portrait is given by this curve. When the straight line gu is moving away from origin, then this straight line gu intersect with the curve hu only at the point this and intersecting point and draw the perpendicular to u axis. So you get only one equilibrium point u3. Corresponding phase portrait is given by this. So u3 is the stable equilibrium point. And if we rotate the line anticlockwise, then u2 and u3 coincides at some value of r, and then upper equilibrium u3 will disappear if r is reduced to further. Here again we will obtain a single equilibrium point u1. When are this is the straight line HU move towards the origin, moves towards the origin. Then you see the straight line intersect the curve GU only at the point, this point, and so we get one equilibrium point U1, and then the phase portrait is given by this is the U1. Here is the stable equilibrium point also. Note that the intermediate equilibrium point U2 collides either with U1 or U3. When U2 coincides with U1, then Budworm density suddenly jumps to higher density U3, implying the outbreak of Budworm population. This is the outbreak of the Budworm population. In other case, when U2 coincides repetition here, coincides with U2, then the Budworm density suddenly jumps to the lower density U1, implying controlled Budworm density. As
স্যার
বলো,
স্যার বলছি এই আউটব্রেক কথাটা বলতে কি বোঝাচ্ছে, মানে ওর মানেটা কি আউটব্রেক?
আউটব্রেক মানে হচ্ছে তোমার হঠাৎ করে মানে প্রচুর সংখ্যায় বেড়ে যাচ্ছে। আউটব্রেক মানে হচ্ছে প্রচুর সংখ্যায় বেড়ে যাচ্ছে, হঠাৎ করে বেড়ে যাচ্ছে। একটা সময় অল্প অল্প দেখছিলে পপুলেশনটা, যেটা ওই ফার ট্রিকে মারাত্মকভাবে ক্ষতি করে দিচ্ছে। মারাত্মক। এখন এই গ্র্যাফগুলো বোঝা খুব শক্ত আছে, এগুলো তোমাকে আরো ধরে ধরে পড়তে হবে এবং বুঝতে হবে। আমি তো তাড়াহুড়ো করে ছেড়ে দিচ্ছি ক্লাসগুলো, এগুলো এত সহজে বোঝা যাবে না, বেশ শক্ত জায়গাগুলো এই জায়গাগুলো। হ্যাঁ, আমি দেখছি আবার যদি পরে একটু বসা যায় এগুলো নিয়ে, এই গ্র্যাফগুলো মানে তোমাকে ভালো করে বুঝতে হবে জিনিসগুলো কিভাবে হচ্ছে জিনিসগুলো, কেন এগুলোকে আউটব্রেক বলছে বা কি বলছে। আমি একটু পড়ে দিই, পরে আমি সময় পেলে বুঝিয়ে দেবো। As dfdu is great positive near u equal to 0 and u is equal to u2, then u equal to 0 and u equal to u2 are unstable, and dfdu is less than 0 near u equal to u1 and u equal to u3, then u equal to u1 and u equal to u3 are stable equilibrium point. So here is draw the graph, and second graph, from the second graph we get the phase portrait in the different cases. So in the first cases, so that the HU is the graph and the curve, and this straight line, this GU. If you GU, notice that if you straight line here, then this straight line intersects with the curve HU only at one point. If you straight line move away from origin, so here Q point is fixed. Q point is fixed on this. Q is the point carrying capacity is fixed. So R is the rate of this Budworm growth rate, and then non-dimensional growth rate. So increasing of non-dimensional growth rate R is increasing towards in this direction. So this straight line intersect the curve HU at these 3 points. So when straight line in this position, we get 3 points U1, U2, U3, and then further increases from the anti-clockwise direction, clockwise direction, to increase the straight line, and you get the straight line touches the curve HU at this point. So this point U1 and U2 coincide this point, and U3 is this here. So from this straight line you get two equilibrium point, this and this, and on the when straight line is in this position, so get this. So when you get 3 U1, U2 and U3 from this position, so from this position of the straight line you get the phase portrait for this position, this U1, U2 and U3. For this phase portrait is given by this graph. For this straight line is here U1, U2, U3, three equilibrium points, and then we get the phase portrait. This graph is three equilibrium points, that is du d tau along the vertical axis du d tau. So that is equals to fu equal to r into gu into hu, and this is this. And for this position, or when this straight line in this position, then you get the this phase portrait is in this position graph, and only this only the intersecting point, stable equilibrium point is this, intersecting with the u-axis. When straight line is in this position, lowest position, you get only intersecting point at u1, and that is u1 shift to this point, so you get this curve, and the only intersecting point u1 which is also stable. So here we see that this u1 is stable and u3 is stable, but u2 is unstable. And also origin also unstable. Here from this graph. So from the figure 5, this the q parameter q along the horizontal axis, and r is the vertical axis, and we get this the curve, this point P, this cusp point, and if r is equal to half, this straight line r equal to half, and this straight line, vertical straight line, and that is q equals to q0, say a point A. So along the curve A, B, C, D, and we get this the equilibrium points u2 is equal to u1, and this curve u2 is equal to u3, and in this region, dotted region, we get three steady states, u1, u2, and u3, and outside this region, in this region, we get only one steady state u1, and in this area we get the one steady state u3 only, and in this shaded region we get three steady states u1, u2, and u3. This is the bifurcation diagram in RQ plane. R and Q are the non-dimensionalized parameter here. The critical value of R and Q are where two roots of the equation 6 coalesce means combine and disappear. Coalesce, that is combine and disappear, and this will give two critical curves and delineate, that is represent the RQ space into three regions. In the inner region, that is shaded region, there exist three equilibrium points, out of which two u1 and u3 are stable and one u2 is unstable. The unstable point u2 separates two stable points. Below the inner region, there exists one equilibrium point u1 which is stable. Above the inner region, there exists one equilibrium point u3 which is stable. And the explanation of the RQ space in the RQ space, in this region, shaded region, three steady states, three equilibrium points, and outside this, along this curve, where u2 and u1 coincides, and along this curve the equilibrium points u2 and u3 coincides. You can easily see this. So when only steady states u3, so when a straight line is drawn along this line, so we get only the steady states u3. When this straight line is moving, towards origin, so we get two equilibrium points, u2 and u3. Actually, this point coincides with u1 and u2. So from this so this curve represents this u2 and u1 equal. So at this point, when this straight line moves away from origin, then u1 and u2 close. So when this straight line is this, so you get this u1 at this point, and at this point u1, so u2 is this and u1 is this. So and away from origin, uh, at this point, actually at this point, u1 and u2 coincides. u1 equals to u2 coincides. So for this point, we get the curve, the curve in this RQ plane, we get the curve this. And when this straight line towards origin, moving towards origin, then we get three steady states, u1, u2, u3. That is the this is the shaded region here. Again, when these straight lines moving near the origin, so you get only the steady states u1 only. That is, here this is the point u1 only, and intersecting point on the u1 on this curve with the curve hu. So you get the steady states u1 here. This is the steady states u1 here, u1 here. And in the upper portion, when away from origin, so you get only u3 is the only steady states, and this from this space we get the only steady states is the u3. So this is the bifurcation diagram. Along the upper curve, the inner region u2 equal to u1, and along the lower curve, the region u2 equal to u3. At the value of r moves upward with equal to u1 must pass completely through the critical region before the upward jump occurs. It must then return completely through past the lower curve before u2 collapses with u3. Equation 6 has the double root, and the line gu is tangent to the curve hu. Then gu equal to hu and dg du equal to dh du. So from gu equal to hu gives this, and dg du dh du gives this. After simplification, from this equation we get r equal to this, and from this equation we get q equal to this. So there are two parameters, non-dimensionalized parameter r and q can be expressed with the terms of the u, where u is the non-dimensionalized population density n. The cusp point P in the figure 5, where both critical curves meet, and is the point where the derivatives of r and q with respect to u both vanish. This corresponds to the inflection point of hu, which occurs at u equal to root 3. So figure 5, from this figure 5, at the point the cusp, this point P, when these two critical curves, this from this point P is the point P is the point P is called cusp. This point P is cusp. This point, when the two critical point u2 is equal to u1 along this curve, and along this curve u2 is equal to u3, meet at the point P, cusp point. And this point cusp, when so from this graph here, this point is this. So u2 equal to u3 is this here. So when the point u3 equal to u2 equal u1 equal to u2 here, so and this point is here u2 equal to u3, and touch at this point here in this point is the u1 is here for this curve, and u2 and u3 is coincide at this point, and this point is this. So at this point, so u2 and u3, and this point is the middle point here, is the root 3 cusp. So change of this curvature, so concave from downward to convex from downward, concave from downward to concave from upward. So the point of inflection is this point, where u U1 equal to U2, U1, this point is U1 equal to U2, and this point is U2 equal to U3, meet this point. This point is called cusp. This corresponds to the impedance. Putting this value of U in the expansion of RU, we get the cusp point, and there is a domain and shaded region in 4, and this is the in the RQ parameter space where 3 roots of the equation 5 exist. This is the R axis, and this is the U star, that is equal to equilibrium points, and this is the third axis is Q parameter. So this is the parameter R, this is the parameter Q along the parameter Q, and this is the third axis is U star, that is the critical points, that is the equilibrium points. And then if we draw this this three-dimensional surface, we draw this three-dimensional surface. This surface gives the location of fixed point, means the equilibrium points. From A to B, B to C, and C to this C, and then going to D. And when trace back from D to C and C to B, and then jump to B, this point, and this then come to the point A. And the shade of this figure along this the curve in the RQ plane, the shade, the surface of shade of the surface along on the RQ plane is this. Already we draw this figure in the bifurcation diagram before. This is the cusp catastrophe. This model exhibits the hysteresis effect. And suppose we have a fixed Q is equal to say Q0 say, and R increases from 0 along the path ABCD, figure 4. Along the path ABCD from figure 4. So along the path ABCD from figure 4. This is the figure 4. Sorry, figure 5. This is the figure 5. Path along A, B, C, D. Suppose is the Q is equal to Q0 is fixed. This the point is Q0. This point is Q0. Q0 is fixed. And if you go through the point A to B, then B to C, then C to D point. Then from this figure we get if U1 equal to 0 and R equal to 0, the U1 equilibrium increases monotonically with R until C. U1 equal to 0 at R equal to 0. U1 equilibrium increases monotonically with R until C is reached. Until C is reached. Until CA to B to C, until C is reached. And for a large R, this steady state disappears and equilibrium value jump to U3. If we now reduce R again, the equilibrium state is the U31 and it remains so until R reaches the lower critical value, where there is again only one steady state, at which point there is a jump from the U3 to U1 state. In other words, as R increases along ABCD, there is a discontinuous jump up at C, while as R decreases from D to A, there is a discontinuous jump down at B. This is an example of a cusp catastrophe, and which is shown schematically in figure 5, where the letters A, B, C, D correspond to those in figure 4. Note that figure 4 is the projection of the surface onto RQ plane with the shaded region corresponding to the fold. The smaller steady state U1 is known as the refuge equilibrium, while U3 is the outbreak equilibrium. We should be done to try to keep the population at a refuge state rather than allow it to reach an outbreak state to control the pest, that is budworm. If flowers were spread to discourage the budworm, this would reduce Q as Kb. The carrying capacity in the absence of predators would be reduced. If the reduction were large enough, this could force the dynamics to have only one equilibrium, that is, effective R and Q do not lie in the shaded region in figure 4. Alternatively, we could try to reduce the reproduction rate Rb or increase the threshold number of predators, since both reduce R, which would be effective if it is below the critical value for U3 to exist.